All right, let's talk about something pretty amazing. How do you see something that no microscope, no matter how powerful, can actually show you? I'm talking about the size of individual molecules. Well, today, we're going to dive into a technique that does just that. We're going to make the invisible visible. And believe it or not, all it takes is a laser and some really, really clever physics.
Okay, so here's how we're going to break it all down. First, we'll tackle the big problem, the nanoscale challenge. Then, we'll see how scientists started shining a light on it, literally. After that, we get to the fun part, watching what I like to call the molecular dance. We'll learn how to decode those dance moves and, most importantly, why this dance matters so much in the real world.
So let's start with the big question. Imagine you're a scientist, and your job is to work with things like proteins, antibodies, or these tiny things called nanoparticles. You absolutely have to know their size. But here's the catch. They are incredibly, mind-bogglingly small. We're talking just a few nanometers across. So how on earth do you measure something you can't even see?
Well, for a long time, the tools for the job, they just weren't very good. You had techniques like denaturing gels, which, get this, would actually destroy the very protein clumps you were trying to measure. Kind of defeats the purpose, right? Then there was another method, size exclusion chromatography, but it had this one huge fatal flaw. It just assumed every single particle was a perfect little sphere. And if you know anything about biology, you know it's messy. Things are rarely perfect spheres. It was clear we needed a much, much better way.
And the solution? Well, it starts with an idea that's almost a cliché, but in this case, it's absolutely true. You just have to shine a light on the problem. I mean that, literally.
The basic idea here is super simple. When you shoot a laser into a liquid that has particles floating around in it, those particles are going to scatter the light. And what's really cool is that how much light gets scattered tells you something about the size and how many particles are in there. This basic method is called static light scattering, or SLS for short. Think of it like taking a single photograph, a snapshot in time.
And don't get me wrong, SLS was a huge step forward. It gives you the average mass of your particles, and if they're big enough, it can even tell you their size. Best of all, it does this without making those silly assumptions about everything being a perfect sphere. But there's always a but, isn't there? It's still just a static picture. It tells you what's there on average, but it doesn't tell you a thing about how the individual particles are actually behaving, how they're moving. And to really understand them, we need to see them in motion.
And this is where things get really interesting. This is where dynamic light scattering, or DLS, comes in and just completely changes the game. See, the real breakthrough wasn't just measuring the light that got scattered. It was watching how that light changes from one tiny fraction of a second to the next.
The big idea is this. Don't just measure the scattered light. Watch how it flickers. Okay, stick with me here. Imagine you're in a pitch-black room. There's one single beam of light cutting through the darkness. Now imagine there are dancers moving all around, but they're completely invisible. You can't see them, but you can see the light glinting and flickering as they move through that beam. That's exactly what DLS is doing, but on a molecular scale. So if you have really small, tiny particles in your solution, they're getting constantly knocked around by water molecules. It's a process called Brownian motion, and it makes them zip and dart around like crazy. As they shoot in and out of that laser beam, they make the scattered light flicker really, really fast. It's this rapid, almost frantic flickering. But now, what about bigger particles? Well, larger, heavier particles are way more sluggish. They just kind of drift through the laser beam much more slowly. So the light they scatter changes slowly, more predictably. The flicker you see is much, much slower.
And this is how we turn a simple observation, the dance speed, into actual hard data. Scientists can measure the speed of that flicker, and they give it a fancy name, the translational diffusion coefficient, or just D for short. It's a precise number that tells us exactly how fast our little molecular dancers are moving through the solution.
Okay, great. So we've measured the dance speed, but remember our original goal? We want to know the size of the dancers. So this next part is all about the magic of decoding those dance moves, of translating that speed into an actual physical size.
And it's actually a really elegant three-step process. First, the machine measures the flicker to get that diffusion coefficient D. Then, and this is the brilliant part, we use a famous equation from physics called the Stokes-Einstein relation. You just plug in that diffusion speed, along with the temperature and the thickness, or viscosity, of the liquid, and bam, the equation spits out the size of the particle.
Now, this is a really important point, so listen close.
DLS doesn't measure the particle's, exact physical shape. What it gives us is something way more useful, called the hydrodynamic radius. Basically, it's the size of a perfect sphere that would move through the liquid at the exact same speed as our particle. It's the particle's effective size, how big it acts as it moves and tumbles around. It's a much better measure of how it behaves in its environment.
Okay, but wait a minute. That all sounds great if all of your particles are exactly the same size. But what happens in the real world, where your sample might be a mix of different sizes? A whole mixed crowd of dancers. How does DLS deal with that?
Well, it gives us another super useful piece of information, something called the polydispersity index, or PDI. The easiest way to think about PDI is as a uniformity score. It tells you if all the dancers in your sample are the same size, or if you've got a wild mix of big ones and small ones all jumbled together.
And what's so great is how simple it is. The PDI value gives you an instant quality check. If you get a low number, say less than 0.1, that's fantastic. It means your sample is what scientists call monodisperse. It's really uniform. But if that number starts creeping up, especially above 0.3, that's a big red flag. It tells you the sample is polydisperse, with a whole bunch of different sizes, and that can mean you have a problem.
All right, so we've geeked out on the physics, which is cool. But why does any of this actually matter? Why do we care so much about the size of these invisible particles? Well, it turns out that understanding this molecular dance can quite literally be a matter of life and death.
This quote really hits the nail on the head, especially in the biopharmaceutical industry, where they're making these incredibly complex drugs. Everything, and I mean everything, comes down to patient safety. You have to be sure that the medicine is stable, that it's pure, and that it's going to work. There's just no room for error.
And the single biggest enemy they fight against, it's something called aggregation. That's a fancy word for clumping. It's when the individual protein molecules in a drug start sticking together, forming bigger and bigger blobs. Now, in a best-case scenario, this just makes the drug stop working. But in a worst-case scenario, these clumps can cause a really dangerous immune reaction in a patient. And DLS, it's one of our best frontline tools for catching this before it ever becomes a problem.
And this chart shows you the power of DLS perfectly. This is from a study on a major antibody drug. Researchers used DLS to find the absolute best conditions to keep it stable. They tested it at different pH levels and measured what's called the onset temperature, basically how hot they could get it before the protein started to clump up. And look at the data. It's crystal clear that at a pH of 5.5, the drug was way more stable. It could handle more heat, which means it's a safer, better medicine.
So let's wrap this up with the key points. DLS is all about measuring those tiny, rapid flickers in scattered light. Those flickers tell us exactly how fast the particles are moving around. From that speed, we can calculate their effective size, their hydrodynamic radius. And all of this makes it an absolutely vital tool for making sure our modern medicines are safe, stable, and effective.
It really makes you think, doesn't it? Just by figuring out a clever way to watch this invisible dance of molecules, we've made life-saving medicines safer for everyone. So that leaves me with one final question for you. What other invisible dances are shaping the world around us, just waiting for us to find the right way to watch?